So now let me go through this more carefully. It's very important, the continuum limit. And do it in a clean way, which will be then to you recognizable as a Fourier transforms, Fourier series and Fourier transforms, then you already know, but now you'll see that that's the same thing. So let's do a little gymnastics in various steps. So first step will be roots of unity. So you know that 1 minus x squared can be written as 1 minus x, 1 plus x. What about 1 minus x cubed? Well, you can write as 1 minus x, 1 plus x squared. You know, when you multiply this minus x, causes cancellations of intermediate terms, and the only terms that survive are this one and the last product. So you immediately figure out that if you have 1 minus x to the n, you can write it as 1 minus x. And here you have 1 plus x squared plus dot, 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 x n minus 1. So now we have a simple formula that says if I have a sequence, the finite number of terms, I can always write it as 1 minus xn, 1 minus x, as long as x is not equal to 1. If it's equal to 1, then, you know, I'll have to think. I notice that if I let x be e to the pi I over, so I replace this x by any root of unity labeled by n, then I get a formula that the sum can be written in this form. And what I have upstairs is I, you know, there used to be an n here, but there is an n there. They cancel. I immediately write down this is 0 if n, the root of unity that I'm using, is not equal 0. But it's indeterminate because if n equals 1, you know, right-hand side has 0 over 0. But then I look at the left-hand side and I observe that n minus 1 m equals 0. All of these guys are exponential to power 0, so they're ones. So this is just sum of n's. It turns out this representation, if I know both sides of it, gives me a formula. It says the sum over n minus 1 m equals 0 e to the 2 pi m over n for any root of unity. We got the Kronecker delta again, but now we got it. Last time I did it by picturing a complex plane, and I argued that the roots point in various directions. And when I average all the roots, I get 0 unless they're all equal to 1. Now you got it from a simple algebraic identity.